Artemis, the sister of Apollo. She will soon be returning humans to the moon. The decades of development are nearly complete. New hardware, new ways of making the journey, and new goals have been set. This time, the United States will not be going it alone. This time, it's an international effort. The first major test will be Artemis 1, an uncrewed journey to the moon and beyond, a final hardware shakedown for manned flights.
Nowadays, astronauts, engineers, and scientists are very excited to go to the moon because it's pure exploration. It's discovering terra incognita. We would go to regions that were never been, well, explored by a human, neither robotically nor in person. The moon is really our 8th continent, and it's there to be discovered. Last time humans have been there was in the 60s and 70s, and they covered, well, 12 people covered 6 landing sites, and imagine that in an area that's so huge. It really doesn't give us a lot of knowledge about the moon itself.
2, 1.
This lunar spacecraft comprises ESA's ESM and NASA's Orion crew capsule. It will be used for an uncrewed certification flight, performing a 6-day orbit around the moon.
We returned to the moon for various reasons, different technologies, and it is a big achievement, I believe.
All over in Europe, we have companies in 10 countries helping to put this ESM together, which is quite significant. And actually, there are hundreds and thousands of people working within Airbus, but also in our partner companies, to make this endeavor a successful mission.
Monitoring of the performance of the ESA segment will be conducted here at ESTEC in the Netherlands.
And that one is only on one side.
These folks here are specifically taking care of the European Service Module, which provides the human capsule part of that with all of its power and life support. So this team here is really taking care of the crew that will be going to the moon and beyond.
I mean, okay,
so there are mainly 2 types of support. That's basically 2 types of situation. Nominal situation, everything goes fine. Here we are actively supporting, actively monitoring the spacecraft, looking at the trend of the parameters to try to predict as much as we can if something is, if a failure is building up or if everything is nominal. And again, anticipation is the key, meaning that you have to know your mission and you have to know what's coming up, what's coming next, for instance, if it's, and then things you cannot predict, and that's why we are training with failures in the simulations. These are failures. And to failures, how we react, how we talk on the voice loops, how we communicate throughout the position between the various subsystems to quickly identify what is the failures, to investigate it, to understand the root cause, and also any likely impact onto the other subsystems, on the system, and also on the mission.
I mean, that's human space flight, and you're always going to have anomalies. We don't say a problem. A problem is indicative of something you don't know that, but anomalies come from in engineering. You can find them, solve them, and continue on. And that's what the teams have been working through recently through the wet dress rehearsals. There was 4 dress rehearsals to make sure everything's absolutely right.
Anyway, you can do like this.
Yeah, you can.
If you click shift.
Today's simulation is what they call an inspection simulation. So the idea is during a launch, they will do a systematic inspection of the entire spacecraft. The European Service Module sits on top of the NASA SLS rocket. So basically, on a pre-launch check, they'll just really systematically look at every piece of those vehicles, trying to identify any potential anomalies or such before they fly.
The surface of the moon has about the same area as Africa, and we only visited the moon 6 times in the 1960s and 1970s. So if you think about landing in 6 different spots in Africa, you quickly realize that there's so much more left to learn and understand about how the moon formed and how it's evolved over the last 4.5 billion years.
Before NASA's Artemis astronauts go to the moon, a small spacecraft called Capstone is leading the way. This small spacecraft will test a unique lunar orbit that has never been flown before. This orbit will be home for NASA's Gateway elements.
Behind me is a mock-up of the Habitat and Logistics Outpost, or as we call it, the HALO module. The HALO module and the power and propulsion element will be delivered to lunar orbit to make up the first components of NASA's Gateway. The Gateway is going to be crew-tended, where crews will visit the Gateway for a period of a few weeks or a few months. HALO and the PPE are just the first components of the Gateway, with plenty of room for future growth. Northrop Grumman has been delivering cargo to the International Space Station using the Cygnus spacecraft since 2013. That's 15 missions and counting. We are now using that Cygnus experience and our lessons learned in the design of the HALO module.
With the power and HALO modules in place, the Gateway will be built up over several launches. The IHAB module will be delivered by the first manned Orion mission. A logistics module with the Canadian robotic arm will be next. The lunar landing system, then Artemis 3, will deliver the refueling infrastructure and telecommunications module before proceeding on to a landing at the lunar southern pole. Before any descent attempt, a crucial component for Artemis is location of a landing site. Unlike the Apollo missions that landed along the relatively flat equatorial regions, Artemis will be landing at the southern pole of the moon, a far more challenging landing scenario. Six landing regions have been identified, close to the permanently shadow regions where water may be found. However, further exploration of these sites is required to pinpoint the most ideal landing location. This will require the services of robots. NASA is sending Viper to scout the terrain.
Viper is a rover of many firsts. The first NASA rover to map water resources, and it's the first rover to wear a headlight.
Viper will be one of many robots descending on the lunar pole in search of water. Testing these robots is well underway in terrain most lunar-like.
Traditionally, rovers are operated from the Earth. With the lunar gateway being put in place around the moon, there's the possibility of controlling them directly with much smaller time delay. And this opens up for new possibilities for things that you simply cannot do or is much more difficult to do from the Earth. So now we're here in Sicily. We're repeating our experiments on the slopes of Mount Etna. The astronaut is not on the International Space Station. He's controlling from a hotel room here. We have our European Space Operations Center in Germany, in Darmstadt, who are directly overseeing and running the operations. And in the role play, they are pretending to be on the moon, and it's very realistic because the slopes of Mount Etna is a wonderful lunar analog. It looks exactly like the moon. There's beautiful craters, there's rocks, it's grey. So we have the European Space Operations Center able to really immerse themselves in the role play, feel like they are planning traverses and exploring regions of interest on the moon in close discussion with the scientists who also get this full immersion where they see a realistic lunar-like geology, so they can have a real discussion. They need to then communicate this to the European Space Operations Center, who has to then make decisions about how they are going to execute operations, whether they make use of the astronaut for direct teleoperation with a short time delay, or whether they make use of their own tools for planning longer traverses and not wasting astronaut time on this. So this is the type of trade-offs and the sort of things that we want to learn how to do for real when we go to the moon, by playing essentially the scenario, playing the game here on Mount Etna. The astronaut is doing the same as he did on the International Space Station in 2019. So he has a control station which allows him to fully teleoperate the rover. What I mean by that is that he can drive it, he can control the arms with direct feedback. So we have a very immersive control station, which allows him to feel a bit like he's on the surface. The robot is his avatar on the surface. It's designed so that he can touch things with the robotic arm and feel what the robotic arm feels. It's designed so that he can decide whether he wants to drive with the joystick, or he can plan his traverses and automatically do it. He can choose whether he wants to manually pick up rocks, whether he can do it automatically. And we really want to learn from his experience which of these tools he is using, which of these tools he is finding useful in different situations, and how his interactions are happening with the science team, how easy it is to communicate which samples to pick up, how the interactions are going with the European Space Operations Center, when they think it's better that he uses his tools to do it, or when it's better that they do it, how the handovers are working. All of these things is what we're trying to learn here. It's a very complex experiment because it has a lot of stakeholders, a lot of partners, because there's a lot of different objectives. We are trying to validate technologies that have not really been used extensively in space. We have this device we used in 2019. It's the first time something like at this level of complexity has been used to control robots from the space station. We have the whole operational scenario, which involves a lot of parties, this game, which is we're trying to learn a lot from. So this complexity makes it a very challenging experiment, but that way we learn a lot.
We are here at Mount Etna in the frame of the Arches campaign, and this campaign is organized by the German Aerospace Center. So there are multiple robots from the German Aerospace Center, via GES, our robot from ESA, and also other research institutes are actually practicing with their robots how it is on a real scenario. So here on Mount Etna, it is very close to what we expect on the moon in sense of soil conditions and harsh environment, dusty, rocky slopes and loose sand. Our robot is controlled today by an astronaut. For this purpose we invited Thomas Reiter. And for us it's important that's an astronaut because in these scenarios we want to practice what happens in reality. So there would be an astronaut sitting in the spacecraft and controlling a robot on the surface of a planet. And in the past we have done this with the ISS. So we had Luca Parmitano in 2019 with Analog 1, controlling our robot in a hangar in Falkenberg. And here, of course, we are on Mount Etna, moon-like scenario, but it's very difficult to have an astronaut on the ISS controlling a robot here on the mountain, to have all the logistics and everything set up at the same time. But to have a fair comparison, we indeed have Thomas Reiter in the hotel room in Catania, controlling a robot here in a realistic scenario.
Yeah, today was a very special scenario because we tested the cooperation between a ground control, people who are sitting in a control room somewhere on Earth, and the crew that is orbiting around the moon in the lunar gateway. And this specific cooperation turned out to be extremely fruitful. In earlier times, it was always thought that there is either a purely robotic operation, which is exclusively controlled from control centers on the Earth, and the crew doing something in situ, being really on the surface of the moon. And I think what we learn here is that this kind of collaboration that you are doing from ground control on the Earth, a crew that is on board a space station that is orbiting the moon, and a rover that is on the surface, can be extremely efficient and much more efficient than actually if either one does it alone.
Well, it's certainly less dangerous to send a rover to the surface than to send an astronaut. It's also cheaper. It's also possible to not take up so much of their time. You know, astronaut time is extremely valuable, so you can send a rover to the surface, you can let the ground team do all their planning, let them do all the longer traverses, and you get the astronaut involved when it's necessary for maybe the more complex task or the things where he really direct teleoperation, direct control of the robot is more helpful.
Our rover is built by the lab and it's a demonstration rover. So we want indeed to figure out what features do we need in a future space mission. So of course if you control a rover, you need for awareness video cameras for the simple ones. But of course to go somewhere you need a locomotion platform, and it needs to be fitted for this loose soil underground, and to manipulate things, for example pick up rocks or maybe later maintenance of infrastructure, you need robotic arms. And so our robot was constructed with this purpose in mind, to have it controlled by an astronaut with force feedback to perform this kind of tasks. But of course we are also looking in the future, so direct teleoperation is good, but of course we also want to enhance our system by more and more autonomous features. And so there my team developed, for example, automated rock detection, so that the astronaut doesn't need to grasp the rock manually, but indeed that the machine learning algorithm detects a rock, controls the robot to grasp it automatically. And this way we want to step by step increase the capabilities to automated driving, automatic obstacle detection, rock detection, to come actually from a remote operated system to a more autonomous system. Today we try to achieve a a full control and a full scenario of our robot. So in the past experiments, we went always step by step. So we had the force feedback device on the station, we had the robot in a controlled environment, and indeed this is one of the first times we put out the robot in a really harsh environment here on Mount Etna. So it's moon-like, we have a complex scenario with the operations center in the background, the astronaut with time delay in the control center, and indeed a task that has been prepared by the team in Darmstadt that was not known to the scientists and to the astronaut beforehand. So here we really try to get as close as possible to real scenarios with surprises in a hard environment. And if we master this, we are really confident that these technologies can be developed further to make it space grade, to indeed be part of the next moon mission.
In our scenario, which is based on a notional mission based on the European Large Logistic Lander, the astronaut, in collaboration with the European Space Operations Center, would be collecting the samples, bringing them back to the lander, and then they would be brought back to the gateway or directly to Earth for analysis by the scientists.
Autonomous robotics will be used not just on the moon, but farther afield. Plans are underway with the Mars Sample Return mission. Landers and launchers are being developed for this mission that will see an autonomous robot, or even perhaps helicopters, that will land on Mars and pick up the samples collected by the Mars rover. Once brought back to the lander, they will be loaded onto a launcher, returned to orbit, collected by the orbiting vehicle, and carried back to Earth via a small re-entry vehicle holding the precious cargo.